In our previous episode, we explored how chaos theory introduced concepts such as self-organizing systems, where minor details can lead to significant impacts due to complex interactions. Additionally, in the Emergence of Life episode from Season 1, we looked into how the chaotic yet structured interactions of atoms and molecules could have set the stage for the origin of life. Now, we take a step further into our exploration of the intricate dance between inorganic chemistry and the living systems that have emerged from it. Where does this order come from, and how do the rules of complex systems foster the leap from non-living to living? A key concept we must analyze deeper is that of self-organization, a principle that suggests components of a system can organize themselves without external direction based on simple rules of interaction. Self-organization is seen in crystallization, a non-living process, yet it shares resemblances with biological patterns. The RNA world hypothesis proposes that RNA, not DNA, was the first replicator molecule. RNA is capable of storing genetic information like DNA, but it can also act as a catalyst like proteins. This duality could have allowed RNA to replicate and evolve without the need for the more complex protein machinery that modern cells use. The discovery of enzymes made of RNA that catalyze their own reactions adds credibility to this theory. Self-replication of RNA chains might have been the precursor to life as we know it. But where does this self-replication fit into the broader context of complex systems? To answer this, researchers look at autocatalytic sets, networks of molecules where each molecule is produced by a reaction within the network, thus leading to the production of themselves indirectly. These networks can grow and evolve, much like living organisms. Recent experimental breakthroughs have led to the creation of a self-sustaining autocatalytic chemical network, marking a significant step toward replicating the precursor processes of early life. In numerous experiments, scientists have observed molecules spontaneously forming networks that are capable of self-replication and mutation. In Stuart Kauffman's book, Exploring the Origins of Life, wherein life emerged from inorganic matter through self-organizing molecular systems, he proposes that autocatalytic sets of molecules, capable of mutually catalyzing each other's formation, may have spontaneously arisen from a prebiotic soup and evolved into early life forms. His key insight is that biological systems are so complex, with such an enormous number of possible states, that only a minuscule fraction of these states are ever realized. Consequently, the particular forms that life assumes cannot be precisely predicted using mathematical determinism. Instead, they might be understood through statistical distributions that reflect the processes of evolution. He posits that a comprehensive understanding of physics must include the study of complexity across various disciplines, or that physics cannot fully explain the emergence of life. Kauffman's doubts about classical physics' ability to elucidate life's origins may encourage us to reimagine our scientific approach, embracing the peculiarities of quantum physics to fill in the blanks. Theoretical investigations suggest quantum principles could be fundamental to life's emergence, as evidenced by potential quantum effects in biological processes highlighted in the preceding discussion. The question now is whether phenomena such as quantum coherence and entanglement might bridge critical gaps in our understanding of prebiotic chemistry. By going into the fine line that separates structured stability and disorder, at the edge of chaos, quantum biology might help us understand how life started in the early simple conditions of the universe. While staying grounded in current scientific understanding, we can imaginatively explore the chance that quantum effects like superposition and entanglement may play undiscovered roles in living systems. If future evidence someday points to quantum processes assisting in the self-organization of intricate biological structures, it could shed light on how complex order arises from simpler pieces in the mystery of life. For now, this remains speculative, but nature has surprised us before. Therefore, we have to explore the intersection of classical and quantum realms in chemical reactions. Chemical reactions are complex processes that straddle the line between the predictable macroscopic world of classical physics and the probabilistic microscopic domain of quantum mechanics. While understanding these reactions, scientists face intriguing questions about the scale at which observable properties transition from being dominated by quantum effects to those governed by classical physics. This has prompted a deep examination of the forces at play within matter's most minute components, alongside those shaping its bulk properties. In the classical realm, chemical reactions are characterized by measurable macroscopic properties like temperature and pressure, values averaged over myriads of atoms and molecules. According to principles of thermodynamics and kinetics, reactions progress along paths determined by factors such as activation energy. Classical models are indispensable for engineering and industrial applications where large-scale phenomena are of greatest concern. In contrast, the quantum realm paints a different picture, one where particle-wave duality and quantized energy levels reign. Quantum chemistry delves into the electronic structures of molecules, utilizing the Schrödinger equation to predict their reactivity and to understand bond formation and cleavage. This microscopic perspective highlights the role of electrons, orbitals, and phenomena such as tunneling, effects without classical parallels. What then is the threshold between these realms? The answer is not clear-cut. It is a complex interplay depending on the system's size, temperature, reaction complexity, and specificity of quantum phenomena. In small systems or low-temperature conditions, quantum effects are pronounced. Conversely, larger systems and higher temperatures tend to mask them, rendering classical descriptions more appropriate. Additionally, timescales matter. Quantum events unfold over femtoseconds, while chemical rates are often observed over much longer periods. The intriguing loss of obvious quantum effects in more complex reactions arises from the interplay of averaging, decoherence, classical path dominance, irreversible timescales, and large-scale quantum predictions aligning with classical outcomes. As reactions become more involved, with multiple intermediates and pathways, individual quantum peculiarities average out. Decoherence rapidly imposes classicality as quantum systems engage with their environment. Despite this, the nonlinear nature of certain chemical processes, such as autocatalytic sets, suggests that on occasion, minuscule quantum fluctuations could resonate through the macroscopic landscape of a reaction. Nonlinear dynamics can amplify small-scale quantum effects. However, decoherence remains a formidable barrier. Within the precisely controlled confines of biological cells, some speculate that quantum mechanics might play a more extended role. Enzymes and photosynthesis hint at the intriguing use of quantum tunneling and coherence. Biological systems theoretically could shield quantum coherence better than unregulated environments, potentially altering the expected scale at which quantum effects diminish. Yet the transfer of quantum effects to larger biological scales remains a topic of active research, with conclusive evidence still on the horizon. While intriguing examples exist, the prevalence of classical physics at macroscopic extents, influenced by the relentless force of decoherence, suggests that biological systems, like non-biological ones, are primarily governed by classical laws. In sum, the narrative of quantum and classical realms in chemical reactions is a continuum where both interact and influence each other. The balance between these realms depends on a host of factors. Although the threshold often leans heavily toward the decoherence and averaging powers of classical physics. Nevertheless, the tantalizing hypothesis that biology might stretch the quantum realm further than anticipated continues to spur scientific inquiry into the enigmatic and subtle dance between the quantum and the classical. Where does this leave us? Understanding the precise pathways from the primordial soup to the first cells remains elusive. We're beginning to piece together the puzzle, with every new discovery shedding light on the processes that may have occurred billions of years ago. It might be that such hypothesis will remain untestable. If so, is there value in pondering and discussing these concepts? This is what we intend to examine in our upcoming episode. Stay tuned for episode 6, where we will see if a purely physical framework is enough for understanding the universe, or if it inevitably needs with metaphysical discussions.